We will now visit an important application of double integrals, and in this lecture we are going to see how double integrals can be used to find the area that is trapped between two curves whose equations are given in terms of x. The lower curve has an equation of y is equal to y sub 1x, and the upper curve has an equation y is equal to y sub 2x. So this is our problem. We want to find this entire shaded area that is trapped between these two curves between two boundaries of x set, x is equal to a and x is equal to b. So that is how the problem can be enunciated, to find the area trapped between two curves whose equations will be given, and two values of x are given, x is equal to a to x is equal to b. Actually, we must recognize that the area that is trapped has four boundaries and four borders. One is the upper curve. So if you put, if we put some dots here to identify the area, the four dots have four boundaries actually. The first boundary is the upper curve y is equal to y 2x. The second boundary is y is equal to y sub 1x. So two of the boundaries are curved lines, they are curved walls. This x is equal to a, many students believe that it's just a value on the x-axis, and x is equal to b is a value on the y-axis. But it's important to realize that when we talk of x is equal to a, in a two-dimensional plane, it actually is this line, a line that is parallel to the y-axis and at a distance of a units from it. So this is actually a. So this is the line, or this is the boundary that is defined by x is equal to a, not a simple point only. Similarly, if we take x is equal to b, x is equal to b is nothing but this particular boundary. So that is the description of the problem. We will get the value of this integral, and for that we have considered a slice, a very thin strip. Actually, we have to show it with a finite amount of gap between these 2 points, but the strip is very narrow, and we are going to cut up this area that we need into an infinite number of such strips. So we start by cutting it down to finite strips and then letting the number of strips increase to infinity. A typical strip has, for its borders, part of the curve y is equal to y 2x and part of the curve y is equal to y 1x, and this is a value that is taken x is equal to x, a typical general value of x, and the neighboring value is x plus dx. So this strip width is just dx. Now one can easily see that the area of this particular strip, we can write, we'll rub out this part and write the area of the strip shown in the figure is nothing but y 2x minus y 1x into strip width. The y 2x minus y 1x gives us this value, and that multiplied by dx is an approximation. Actually, we should write approximate area. approximate area of the strip is y2x minus y1x dx. Now, it is easy to imagine that the total area that we are looking for is the sum of such an expression starting from the leftmost value of x and going all the way up to the rightmost value of x. So, that is what we call integration. So, this area required, now we can write infinite summation of such strips. Infinite summation meaning that the number of strips that we slice out this area into is going to be infinite. It is not summation of 5 or 6 very large strips or 10 or 11 or whatever, but an infinite number of strips, each strip width becoming infinitesimally small. So, an infinite number of strips, each of which infinitesimally small, and that is in spirit nothing but the integration. Infinite summation is integration. This we have learned in high school, so that's not a problem. So, what we will do is we will integrate such like expressions from x is equal to a to x is equal to b, rub out the part of the top, the enunciation of the problem, and write the result, that is the bottom line, saying that the required area is equal to y2x minus y1x dx, with x starting from a and x going all the way up to b, so that the entire area is covered. And this can be used as a standard formula for finding the area under x is equal to under y2 and y1, trapped between them, not under any one of them, and between x is equal to a to x is equal to b. We will see an application, and we'll also try to see how this can be merged into a double integral. Actually, it looks to be a single integral only, but then I will give the area as a double integral as well. Let us see. We take a simple example where we've said find the area enclosed between y square is equal to 4x and x square is equal to 4y in the first Q, meaning in the first quadrant. Now, it is important to emphasize that when we find or try to find the area that is trapped between two curves, between set values of x is equal to a, x is equal to b, we must be able to visualize the area properly, and for that we need to draw a diagram. The diagram also enables us to set the limits of integration, which are very important. So, not only do we see the shape of the curves that are involved, the two curves that trap that area which we are looking for, but we also get information as to how to set the limits, without which of course we cannot reach home. Home meaning the actual answer. So, let us see, we will draw these two graphs, y square is 4x and x square is 4y, which are basically parabolas. We have learnt in high school that these are parabolas. I will try to first generate the two curves and see what area we are talking about. We take a y-axis and we take an x-axis. Now, all of us know that the parabola y square is equal to 4x is one that is lying down with its axis coinciding with the x-axis. So, if this is the origin, if this is the x-axis, and this is the y-axis, then the first parabola, that part which lies in the first quadrant, is something like this. The entire parabola goes down like this, but we are talking of the first quadrant only, so we don't draw the entire parabola. Similarly, x square is equal to 4y. We just interchange the roles of x and y in this parabola, and we will get something like this, in which the axis of this parabola coincides with the y-axis. This parabola is symmetric about the y-axis, and the first parabola drawn is symmetric about the x-axis. Now, so this curve is y square is equal to 4x, and this curve is x square is equal to 4y. Now the first thing is that both the curves pass through the origin. That's very evident. Once we plot it, or from our previous knowledge, we can see that both pass through the origin, and then we must find the point at which these two curves intersect. That is very important, and that will give us the limiting values of x. We see that the point P, whatever its coordinates we'll find out, will have coordinates, actually will have coordinates 4 and 4. We'll find out that. Now, to find the points of intersection of these two parabolas, actually there are 2 points. One is this, which we fail to see quite often, but this is very evident that the origin is also a point of intersection, and that will emerge when we solve the 2 equations simultaneously. So now let us solve the 2 equations. X square is equal to 4y and y square is equal to 4x. When we solve these simultaneously, we can write, for example, supposing we square this particular equation, we'll get 16y square is equal to x to the power of 4. This can be written as 16y square is x to the power of 4. 16y square is x to the power of 4. So when we equate these two, y square can be replaced by x square by 16, and that is equal to 4x. So together these two imply that x4 by 16 is equal to 4x. x4 by 16 is equal to 4x, then this implies x to the power of 4 minus 64x is 0, which implies that x into x cubed minus 64 is equal to 0. Now this is interesting. One value of x that will make this equation 0, the right hand side 0, is x is equal to 0, and that is reflective of this point of intersection. This is a cubic, so x cubed is equal to 64 must throw up 3 values of x. One value of x is evidently 4. X cubed is equal to 64 gives the real value of x is equal to 4. But then there are 2 more values which are actually complex values. One will be 4 omega and the other is 4 omega square. Now they don't lie in the real plane, so we ignore that and come to the conclusion that x is equal to 4 is the x coordinate of this point of intersection, the other one being the origin. Now when x is equal to 4, we can substitute 4 square is 16, and then corresponding value of y is actually also 4. So this point P becomes nothing but the point 4, 4. That's it. So we are partly home. That means we know the limits of the integration, 0 to 4. And what is y2 minus y1? this was taken as y is equal to y2 and this lower curve was taken as y1. So the difference, that means if we take any particular value of x and take a strip like we've done before, then the difference in the ordinates is root of 2x, that is y upper, minus x square by 4, that is y lower. So 2 root x and x square by 4. So we will do a bit of rubbing out and then try to find the integral value. Required area is x is equal to 0, x is equal to 4. The upper curve had an equation of y2 is 2 root x, because y2 square is 4x minus x square by 4. X square is equal to 4y, that is the lower curve. So x square is equal to 4y means y lower is x square by 4. I'll put down the values of the curves. This comes from y square is equal to 4x. This is the upper one. And this comes from x square is equal to 4y lower curve. Y sub u is y upper curve. Y sub L is y lower curve. So once we carry out this integration and substitute the limits of 0 to 4, we will see what we get just 1 or 2 steps away. This becomes equal to 2 times root of x will integrate to x to the power of 3 by 2 divided by 3 by 2. So we will multiply it by 2 by 3 minus x square by 4 will integrate to x cube by 12. The limits being 0 and 4. This is now the first limit is 4 by 3, 4 to the power of 3 by 2, 4 by 3, 4 to the power of 3 by 2 minus 4 cube by 12. So 64 by 12. Now 4 to the power of 3 by 2 is the square root of 4 cube, that is 8. So this is 8 into 4 divided by 3, 32 by 3 minus 64 by 12 is 16 by 3. The result is a net of 16 by 3 square units. Actually, I have taken in this particular case a very special case of a more general problem, which says that show that the area enclosed between y square is equal to 4ax and x square is equal to 4ay is 1/3 of the total area. 4a is 16, a square by 3. So if we take actually y square 4ax and x square is 4ay, these are general case, then this particular area is actually 1/3 the area of this square. Now this square has an area of 4a into 4a, that is 16a square, and 1/3 of that is 16a square by 3. We have taken a as 1. So 16a square by 3 is 16 over 3. So we are home, and that's it for now.